In today's video, we're going to explore the fascinating concept of why falling objects eventually reach a point known as terminal velocity, which is essentially when their speed stops increasing and becomes constant, meaning they are no longer accelerating or decelerating. Since this topic can be a little tricky to grasp, we'll walk through the whole idea step by step and then summarize everything neatly at the end. Let's begin by picturing the exact moment when someone steps out of an airplane. In that brief instant, they are momentarily suspended in the air, completely still. So what happens next? Well, because this person has mass, Earth's gravity will begin pulling them downward, and this pull is what we refer to as weight, a force acting downwards. And because the person's mass remains unchanged, their weight remains constant throughout the entire fall, which we can represent with a downward pointing arrow that stays the same size throughout the explanation. Initially, right as they exit the plane, weight is the only force acting on them. So the resultant force, which is the overall force once all individual forces are added up, is identical to their weight and directed straight down. This unopposed force causes the person to begin accelerating toward the ground. However, as soon as they start falling, another force comes into play, air resistance, also known as drag. This is an upward force caused by collisions between the falling person and countless tiny air particles in the atmosphere. These collisions slow the person down. And the strength of this drag depends mainly on two factors: the surface area of the person, since a larger area means more particles can collide with them, and their velocity, because falling faster means hitting more particles per second. Now, since the person has only just begun falling, their velocity is still relatively low, and that means the upward air resistance is still quite weak, which we might represent with a small gray arrow. At this point, the resultant force is the difference between the constant downward weight and the smaller upward drag, meaning there is still a net downward force, and so they continue accelerating. As the person picks up speed, the collisions with air particles become more frequent, causing the air resistance to grow stronger. Since weight stays the same but drag increases, the resultant force, the difference between these two opposing forces, becomes smaller. The person is still accelerating, but now at a slower rate. If we visualize this on a velocity-time graph, with time on the x-axis and velocity on the y-axis, the curve begins steep but starts to flatten out as time progresses, reflecting the decreasing rate of acceleration. Eventually, the person falls fast enough that the upward air resistance becomes equal in magnitude to the downward weight. At that point, the forces cancel each other out. The resultant force becomes zero, and because there's no unbalanced force acting anymore, the person stops accelerating altogether. This constant falling speed is known as terminal velocity. Now let's imagine the person opens their parachute. Suddenly, their surface area increases dramatically, and so does the air resistance. This causes the resultant force to reverse direction and point upward, which means the person begins accelerating upwards. Or in simpler terms, they start decelerating and slow down in their downward motion. As they continue slowing down, the air resistance gradually decreases again, until it once more balances with the weight. At this point, the resultant force becomes zero again, and the person reaches a new, slower terminal velocity, slower than before because the parachute increased their drag significantly. To wrap it all up in a quick recap, when an object starts falling, it has a large downward weight and very little upward drag, so it accelerates downward. As it speeds up, drag increases until it balances with weight, resulting in no net force and a constant falling speed, terminal velocity. If something like a parachute opens, that balance is disturbed, drag increases, the object slows down, and eventually a new, lower terminal velocity is reached. That's everything for this video. So if you found this explanation helpful, be sure to give us a like and subscribe, and we'll see you in the next one.